Hi everyone, thanks a lot for joining us for this 12th Urban AI conversation. Today we have the great pleasure to welcome Katya Letunovsky, and we are going to talk about urban data and real estate. So my name is Hubert, and I'm the founder of Urban AI. Urban AI is a think tank that federates a global community of pioneers in the emerging field of urban artificial intelligence. Together, we are investigating this concept, and we propose ethical modes of governance and sustainable uses of urban artificial intelligence. But urban AI is also a space for debate and exchange, and this is why we regularly organize these urban AI conversations, during which members of the community can present you the latest research, projects, solutions, as it will be the case today, or even just ID. And so today we'll talk about urban data and real estate with Katya Letunovsky, who is VP and co-founder of HABIDATUM, and also a contributor of Urban AI. As usual, we will have like 20-25 minutes of presentation, and then we will have a Q&A session. So if you have questions in mind, you can either use the chat or wait for the Q&A session and directly open your micro. Katya, the floor is yours.
Thanks very much, Hubert, and hello everyone. Nice meeting you. I'll be talking about, generally what we do as a company, but noting some of the things I believe are important generally for the topic of real estate and AI and their merging together. In terms of location specifically, so the company I operate and founded is focused on location. I'm trained as a geographer and urban planner initially, so I worked a lot with studying the locations, areas, neighborhoods in detail in my past career. And when we founded HABIDATUM back in 2014, the idea was to actually add additional data sources to this kind of analysis. We started working with cities initially on master plans, transport planning, and things like that, trying to find meaningful ways to integrate data from alternative sources that people are not yet used to into the traditional analysis and make practical use of it. So we worked on master plans, thinking about how to integrate the way people move around into considerations for master plans, and transport models, of course. And gradually from that, we moved to just working with real estate, specifically commercial real estate, and financial institutions dealing with that. Just because the data analytics we developed is really transforming this market. And so as of now, we are pretty much focused on that. However, some of the master planning projects still exist in our portfolio. The data we deal with is mobile phone data as the first source. So where people move, where they sleep, where they work in aggregated form only, but the statistics on movement patterns and crowdedness of places, changes over time, those kinds of things we're pretty much experienced of dealing with. And the data comes from two major sources. One is mobile phone companies, like the data that's collected from basic stations that transmit the signals between the phones. And the second data source for that is location-based GPS apps, weather apps, e-commerce apps, taxi apps, and so on, that use location to provide services to the users. And at the same time, when there is a consent, they can aggregate this data and use it for further analytics with the companies like ours. We don't use this data in isolation, so we connect it with the qualities of the built environment itself, with buildings, with travel times, transport accessibilities, with the commercial diversity and activity of areas, and hence There are other data sources that are listed in here that we use, including banking data, including digital maps data, satellite imagery data, and so on. So we just overlay how people vote with their feet with the landscape of urban environment and the real estate landscape, seeing how those correlate between themselves. To make it happen, and so here the AI and technology part starts, we needed to develop, first of all, some kind of platform. This is important because the data comes in very different formats, and we need to have a way to just harmonize it and to make it comparable across locations. Very often, we deal with international portfolios, like real estate investors who invest in different countries, or master planning project that needs benchmarks all across the globe. And in this case, we need to make sure that if we take mobility patterns from, say, Germany and France, we can really compare them to each other. We are not talking about completely different data and completely different behavior. So as a geographer, so I'm putting a lot of focus on, making geography really speak for itself and avoiding data inaccuracies that can spoil this kind of geographic analysis. Besides that, there is a need to make data comparable across time, which is also a very hard issue, and it needs to be solved algorithmically, just because the mobile phone apps, mobile phone companies, banking companies, they always are changing the way they collect data. There can be technical changes, there can be regulatory changes. There are, of course, all the time, new approaches to dealing with the privacy of the users so that the data is always segregated. And due to that, there are changes in the data itself all the time. And so people who analyze it through time really need to account for it and to make this, what we say based on the data, really meaningful by balancing those changes over time. So we really spend a lot of time building algorithms to make this data comparable across geographies and across time periods, so that you can run historical analysis and maybe some forecasting sometimes. So those are two important points I wanted to highlight. The third one, which is also a technological issue and also an analytical issue, is the penetration, the coverage of the data. It's of course not covering each and every one in each and every country. We are dealing with samples, which we believe are still sufficient samples to run the analysis, but to make sure we can do this analysis, we can't just say we believe, right? We need to do checks and analysis if the data is even geographically, if the data is even across socio-demographic groups, right? If it's uneven, we need to balance it. We need to approximate it to total numbers so that we're not just talking about some users of some apps, but instead are talking about, the population. Because for real estate, what matters is not just some user of some app. What matters is really the foot traffic, really the amount of demand for this real estate. And between the initial data and this understanding of the demand, there are many steps that you need to do to really make this data valid and justifiable. So that's where we use our platform. We first aggregate all the data in single format and then run all these algorithms on top. And then we get this ultimate kind of metrics that we can analyze and put in practice. So what these metrics are, so that's about the comparisons across the globe. That's something I told you about already. So what these metrics are, they are about, people moving around the property, foot traffic, people being in the property, like property occupancy or vacancy, how much time people spend in there, dwell time. Like, do people work there, or do people just hang out there, meet their friends? This can be identified using the temporal component of mobile phone data. This is, as I said, overlaid against the commercial diversity and against the transport kind of and walkability parameters of the area. So those are three cornerstones of our analysis: the commercial component, the mobility component, and the accessibility component. All together, all combined, they form our ultimate metric that we call location risk or location commercial potential scoring, which is ultimately the combination of all these parameters transformed into a relative metric, where each location gets a score, a ranking, based on how much diverse, how much active in terms of mobility, and how much well connected it is in terms of transport. I'll be talking a little bit more about that, but just as an initial highlight. So it's important, well, when dealing with all those data points, to also define what we're talking about, what unit we're talking about, when what real estate is when we're talking about such data. So for us, there's no single definition of a location. It's actually a combination of different entities. Each of them is meaningful for real estate analysis in its own way. One is the building, of course. When we're talking about vacancy or occupancy, we're looking within the building. But then if we're talking about the foot traffic, we need to know where would we analyze this foot traffic, where it really makes sense. So we take two major parameters here. One is the closest kind of proximity of the building, which is the grid cell that surrounds it. It can be 100 per 100 meter or 300 per 300 meter and so on. Second is travel time, pedestrian accessibility area or transport accessibility area. Depending on the type of the property we're talking about, there could be different travel times that matter. Like for local retailer, this would be pedestrian accessibility. For a logistics center, a warehouse, we'll be talking about, car and freight accessibility. So those three kind of cornerstones again: a building, its nearest proximity, a grid cell, and then this broader surrounding that's formed by travel time. That's the location in its different components. There's some work that needs to be done to attribute data to these locations. So that's also a technological part that we're doing. It's just maybe what's useful to mention in here is that initial data that comes from mobile phones and GPS is very, very granular in space. Being still aggregated, it's still, really granular in space. So it allows for defining the buildings, for example. If we're dealing with mobile phone data that comes from telecom operators, like, the data that's collected through basic stations, base stations, telephone towers, this data is less aggregated in space, so it's in larger areas, and the building level analysis is not possible in there. So when dealing with GPS data, we can attribute to specific buildings and then map these buildings for the whole region. So here, for example, this is kind of post-pandemic recovery of activity within the buildings on Manhattan. And so the darker the color and the higher the buildings here, the less the recovery is. So the more negative the delta is between what it used to be in pre-pandemic period to what it is now. So actually downtown is still not recovered that well, and upper midtown and the area close to Central Park, same way. Then we can always zoom into a building. And one of the things that I wanted to mention in here is that this kind of alternative mobility data sometimes closes the gaps in other data that's hard to collect. Like, for example, sometimes there are issues with really knowing what tenants move in, move out, when they close, and so on. So this kind of data is inconsistent and hard to collect. So mobility data, occupancy data does not show like exact tenants, right? But it signals where something changes strongly, and then you can drill down to this property and check on the tenants. So it can just filter out those properties that need your attention, where probably something happened, some tenant moved in or moved out, and you need to check that. So you will just be collecting the data on a smaller sample, at least. So in this case, that's an illustration of that. So the diagram should be quite stable, right? The occupancy, if all the tenants are in place. So it should be like all the time, month by month. But here we see first the spike and then a large decline. So for this specific property, what actually happened is that a major tenant moved in. So it's not the only tenant in there, but it's a large attractor. So actually the activity grew 3 times more after that. But then the flood happened and some of the tenants needed to close. And another anchor tenant, just a large grocery store and pharmacy, needed to close. And this led to 3 times drop in activity. And it's still not recovered, even though CVS started opening up closer to the end of the year. It's still, halfway through to the recovery. So this is, the other properties we looked at that are located on a more elevated level. They were not touched by the flood that much, and hence they had more kind of stable activity. Then also looking at this occupancy data, we can see some recently vacant buildings, not just the ones that are all the time vacant and that everyone knows they need, redevelopment or something, but some buildings just randomly become vacant because of, some bankruptcy of the tenant or some other external factors. Those properties attract much attention by insurers, by banks, by more or less all the types of audiences we deal with. So that's really some signal to track, some negative signal to track. And so those kinds of signals can be mapped based on this data. And so that's just one of the examples, like seeing that the property has been occupied, well, with some dynamics, but there were still some people in there, and then just dropped, just nothing, closed its doors. Another thing that can be seen is the real catchment area of the property. And it's actually different from what we think about it intuitively. So here, there is a map on the left side. The gray color shows the census block groups, the administrative areas in which people who visited a shopping mall reside. And this area is in gray color. And then on the right map, on top of this area in gray color, we overlay the pink line, which is the travel time, 10-minute drive. And we could assume that for this local shopping mall, 10-minute drive would be a perfect kind of catchment area. But see, the configuration is completely different. So to the north of the shopping mall, people prefer going to it even outside of 10-minute drive. They can drive 15 minutes and this is okay for them. To the south of the mall, people don't drive 10 minutes. They actually drive probably 5 or less. And the rest of the areas, they just don't go from there. So this configuration is unpredictable in a way. You can't just put it on the map intuitively. You need to see it from the data. And it's possible in an aggregated way, of course. Then what we used it for in our analysis is actually selecting comparable properties. So that when looking at this mall and seeing, does it do well or not, we need to see okay, compared to what? And so we selected the comparables only in this area. So Here is their list, like the shopping malls with similar tenants, anchor tenants within this area. So we created this list. It's done automatically just using this points of interest data. And then we started comparing them by how many visitors are there. Is it recovered compared to what it used to be pre-pandemic? Actually, our subject property looks pretty good compared to the majority of others. And then we also compare them by location risk score. So that's the metric I mentioned in the beginning. So that's the ultimate kind of combination of all the data that we operate: commercial diversity, mobility, and travel time, and relative ranking between the location. Based on its relative nature, it's changing less radically compared to just mobility. And so it shows kind of more medium-term and long-term trends of the locations. And so here we can see that, for instance, the main difference between location risk score is appearing on town level. Properties in the same towns have the same kind of dynamics. Actually, the large properties are improving over time, while New Rochelle properties, for example, are just not changing their location score at all, which is, in comparison to others, a bad signal. So this location risk scoring, just to explain it in more detail, we take mobility and commercial diversity data, we put it in grid cells, we then draw the travel times on top, like 10-minute drive, for instance. Then we aggregate all the data inside this 10-minute drive. And then for each property, we would compare itself with the others, not just based on what happens within this property, but what happens within this travel time. And that gives the scoring. So that's the conceptual scheme, but generally, we take the property itself, we take its travel time with all the data inside, and then we do the comparison. So to us, it's very important to highlight this inclusion of travel time inside this calculation, just because what matters for commercial real estate is not just what happens within the property, it's this catchment area, this hinterland that generates the demand, and it needs to be taken into the consideration if you do some generic scoring or whatever. And so that's why we account for it. And really, this travel time matters. Like, this is the map of Greater New York area with just taking 10-minute public transit area inside. This is one geography. And then we add auto, like car, vehicle mobility. And so this is completely different map and walk score as well. So completely different. So actually looking at this too, like a lot of locations would get different scores, just adding different zones into calculation. And zooming into a location, we can see the structure of its accessibilities filled with people and businesses. Like this specific property has a very good score by car. So all areas that are accessible from this property by car are well populated and commercially diverse. So they're cool. But when you walk from this property, you are actually in a very empty and uninteresting location based on the score that's not one, the best, but three, one of the poorer ones. So there's poor walkable area and public transit area. And that's a signal, if you're thinking about, rethinking this property, that might be a signal of a change of a function, the function that works better on the wider area, not the closer one. And so this is the direction that we call kind of best use, location risk score based best use analysis. And it's where maybe the most important part of the, AI and massive algorithmic calculation happens, because we take all the properties of the same type, all the retailers all across the US, we map them against these types of matrices that I showed here on the slide. And then we select like the best mix, the best appropriate mix for the best performing shops. And then when you will be looking for a place for a new shop, for example, we will only be finding the locations that are not just with much traffic inside, but that have exactly this kind of structure of accessibilities that fits the best shops. Or if you're looking at your area, at your location and thinking like, what function fits here? What should I do there instead of a shop? We can say, all right, so this structure that we are looking at, based on our statistical calculations, fits, dark kitchen very well. So put a dark kitchen in here. And you can always, you can always select, you can always use your creativity, but you have at least some statistical basis for it, and you can play with it. And correlating that to rents or to turnovers helps even forecast the rents and turnovers in the area as well. So yeah, that's where I wanted to end, just wrapping up on how it's applied. It's applied for site selection that I mentioned. It's applied for best use analysis and management of the properties and portfolios. And outside of that, we also work a lot with banks and insurers on just defining the appropriate signals for their risk models. That's probably not the exhaustive kind of list of applications, but at least some general structure of that. With that, I'm glad to wrap up and see if you have any questions. Thanks a lot. That are my contacts.
Thank you. Thank you very much, Katya, for this very insightful and fascinating presentation. If some of you have questions, and I see that today we have a lot of urban AI experts actually, so that's really nice. So Aurel, Laura, Parag, or like if some of you have questions, feel free to directly open your micro or use the chat. Actually, I have a question, Katya, so maybe I can ask as oh, okay, all right, go on.
Thank you for this presentation. I snuck in a little bit late, so you might have presented this, but what is the underlying platform or technology you use to aggregate that data? I'm sorry, I came in late. Can you repeat that in one sentence?
Yes, absolutely. So we initially kind of gather this data from other platforms, from telecom companies or from GPS companies and digital maps as well. Like points of interest data comes from Google, Microsoft Bing, OpenStreetMap, and so the regular sources like that. Satellite imagery we also use, and mobile phone data comes from companies like Etisalat, Vodafone, and so on, in aggregated way. This is telecom data. I talked about that, and then the GPS data comes from mobile app GPS aggregators. So there are companies on the market that we work with, like Uber Media, or they have a new name now, Near, and Spectus. So used to be called Cubic. And there are many more like that, like SafeGraph and so on the market. We are just, collecting the data from them. We're not generating the data by ourselves to make the calculations that I mentioned, like to make data comparable over time and across geographies, to calculate the metrics on top, like location risk scoring. We use our own platform. So we have our own database. It's called Chronotope Grid. It's actually a special temporal database where there are many, many voxels with lat long and timestamp that cover the whole globe. The sizes of the grid cells vary based on the latitude and longitude, but generally, like we can drill down to like kilometers, and we then can drill out and then drill down to like meters. So that's an interactive database that appeared to be helpful to us, and we needed to develop it just because the regular geographic structure, like shape files and all this stuff, was not, interactive enough in terms of temporal analysis and did not allow us for that. And so we developed our own And on top of this database, that's also in-house developed data pipelines, as we call them, and dashboards that we built.
That sounds great. So I totally understood the aggregation of data. You don't synthesize it yourself. You buy it. You scrape it. Then you have your stratified data cube with the voxels. And now I would be interested in the data structure that allows you to retrieve the information, because it's a lot. I mean, of course, you can say, okay, this is my geographic area, so I have a boundary in longitude, latitude, but it's buried in thousands and thousands of seconds of history. So how do you go deep?
We from the initial data, we would collect what has latitude, longitude, and timestamp. What we will do then would be defining the geographic units like buildings or travel time areas. Those are the geographic units. In terms of temporal units, well, mainly the type of analysis we do based on the examples even that I showed deals with the monthly aggregates. So we would be having the data with, this per second granularity, but we would still be aggregating it to the whole month and building some mean values that we then deal with. Sometimes there is a need to deal with hourly patterns, but we never deal with like really real-time data. It is initially real-time, but we aggregate it statistically still. So even the hourly patterns, we would be building on some aggregates like weekly or monthly aggregate. And this helps us smoothen the data. And I talked about that. So the main obstacle of this data is just inconsistency, right? It's changing over time really a lot, and you need to smoothen it before you analyze. So that's what we see feasible on a monthly and weekly basis.
Thank you. Thanks.
Thanks for the question.
Sorry, Laura, yes, please.
Yes, hi Katya. Thank you for that wonderful presentation. I knew HABIDATUM a long time ago through Alexei. I'm not sure if you actually came to visit us, but Alexei did. So he introduced us to HABIDATUM back then, and I had the same question as Arel, but you already answered that in terms of the data. Now, one question that I still have is, how do you deal with new towns? And by new towns, I mean areas from scratch, nothing surrounding that context, which you can actually, forecast. How do you create? You say that you have your own database, but you can create new data. So how do you approach when it comes to a sort of, let's say, tabula rasa, in a way?
Sure. Thanks, Laura, and nice to meet you again. I think, yeah, we should have met at Foster and Partners together with Alexei. Yeah, I think Ed Demetri introduced us at that time. But
yes, correct.
Yeah. So basically, dealing with new kind of greenfield developments is this is not a very common ask from financial institutions. They usually deal with established built environment, but we used to work a lot with that when dealing with urban planning. So like building a master plan for instance, Brainport Smart District. We did it with UN Studio in the south of Netherlands. It's not far from Eindhoven, but in that area, nothing was happening at the time we started the activity. So what we need to do in here is to, like in the traditional analysis, we need to select benchmark areas that look similar and see what we can take out from them. So we just, in a way, kind of automate this analysis. We take out some of the benchmarks from the experts, from our partners, but we then expand this sample, like find similar places that are located in similar location risk scored areas. Then we, within those areas, study like how the flows are distributed, what's the commercial diversity, what's the street network connectivity, how it all correlates. And then that's an iterative process with partners. So there's no like black box prediction tool, but
Right.
we have some approaches of, you know, populating that to the new area.
Okay. Okay. Great. Thank you.
Thanks.
Ariel, I guess you have a question.
Yes, thank you. Thank you, Katya. Very interesting talk, definitely. I'm interested in the transition that you've mentioned at the beginning. You said you kind of moved from this sort of project-based market to something which is a bit more generic, more scalable, more platform-oriented. I'm interested to hear about your, let's say, usual suspect client today, like who would that be? And the second thing is, what is within all the platform and the tools that you've mentioned, what is the one thing that they want the most? Like, what is your key product there? To the degree you can disclose, I guess.
Yeah, of course I can. And the reason for us to move from this project-based approach is to, you know, to more scalable one is just with, probably as with every company that deals with technology, when you feel that your technology gets productized and you really can, you know, repeat it on scale, not just do a project, you do that. And that's what we did. And actually, like, we are large fans of Esri, like the GIS giant, right? And they started the same way. They were around landscape analytics and did projects, and then they became like the largest GIS systems company in the world. And this is like kind of the example that we want to follow. But in terms of the current clients, so we are targeting those who have transactions, like you know, repeated kind of actions that always require data. So our best customer would be insurer, because they really do a lot of policies, and for each of the policies they want to, you know, analyze the risk, and if the data fit into their risk model, this is just, you know, just repeated kind of flow of transactions that happens. So this is why we target insurers a lot in our product activity and current projects. In terms of, I also wanted to add something. In terms of the type of product that's of the best use for them. One is location risk score, as it's more generic and it kind of shows the real risk of the area outside of local shocks. This is important. The second is more dynamic. So vacancy and occupancy of buildings, I would say, is one of the most popular, because it really shows like the breadth of the market, right? The real-time breadth. So those two components, they really marry well, just because you need the medium-term trend and the current breadth. And so vacancy and location risk score is just a good combination for that. Yeah.
Excellent, thank you.
Thank you. I just switched my laptop into charger, just 1 second. Sorry. Yeah.
You have a
Yeah, I have two questions. Thank you, Katya, for your presentation. It was very interesting. I just wanted to understand better, how do you characterize the building? Because you said you talk about the building, then you move to the cell, and then you have like an area that, like for example, you said a building is characterized by the occupancy that you have, that you get from the mobility data, plus the walk score that you get from walking or using a bike or car. But I was curious if you consider also the amenities that are around. Will a building be also characterized by the many houses that are around, or the many, if it has, I don't know, schools or any other infrastructure? Have you considered thinking of the building not only by these two let's say, type of data that you're working on, but other things that we talk about.
Yeah, thanks a lot for this question. This is really an important component. We call it commercial diversity, but it's split actually into types of functions. So we look at points of interest like, cafes, schools, parks, fire stations. When we combine all of them together, we call it commercial density, like how many functions are there overall in a given area. And commercial diversity, how many functions of different type are presented in there, because you can have like very high commercial density, but these are all the same groceries, right? And this is not diverse. The more diverse the area is, the better it stands against shocks based on what we've seen in the data as well. So commercial diversity is a large component. But for insurers, for instance, it's important to see specific kind of functions within the accessibility, like fire stations, like repair services, like plumbers, and so on. So you want to see them, how many of them are reachable by car. Like we did this kind of calculation, based on how far away the fire station is, you can really understand like what damage from the fire would be in a building within the time this fire car will be able to arrive to this building. So this kind of calculation, yeah, is possible.
I was asking because you show at the end these regression models that you're running with your database, which is populated by these many, you said you took the US and then you took every single building and then you characterized it in this particular way. I was thinking, have you tried clustering algorithms, like, to try to, because you said like you identify a type and then you can predict this for a next space or next city based on what you learn. I was curious about what is the method, what is the algorithm that we use for the prediction. Are those, I was guessing those are like clustering algorithms based on the vector that you have for each building, or could you explain a little bit more about that?
Yeah, I'm afraid to tell something illiteral here, because I'm not the one who's doing the majority of the data science work myself. I'm on the geography and kind of urban planning side. However, the data analysts that work on these algorithms, they definitely use clustering for sure, at least geographically. In terms of this vector analysis and defining similarities and dissimilarities between the locations based on it. So we are definitely applying that and we used to apply that for urban planning reasons. Is it exactly the method that's applied within this POI, this location risk score, this rent analysis? I can't state for sure now, but probably something around that. So I can just specify that with our data scientists and maybe share with Uber based on the discussion as a follow-up, just as you're curious an exact method that's used in this analysis. But the vector analysis overall, we've used it a lot also when dealing with semantic data. I didn't mention it a lot just because we're not using it in our current analysis a lot. This data is no longer well accessible, like Twitter or Instagram or something around that. But in our early years, we worked a lot with social network data, and we collected like what people talk about with regards to certain locations. And there we applied vector analysis a lot to identify like similar word contexts for words and to define the topics of discussion, something around that. So,
thank you for your question.
Yeah, thanks.
Jeremy, you want to
Jeremy?
Hi, thanks for the very interesting talk. I had a quick question about sort of the data processing that you were going through with respect to the individual voxels that you've developed, like within your company, versus the data that you're then imposing into those voxels. Because we use a lot of shape files, etc., to do similar types of data merging at different scales. Looking at a metropolitan area or a census tract level to be able to report at those different levels. But we found a lot of benefit in combining kind of like different data sets together. I'm wondering what's your strategy for merging data sets between that are sort of like, I understand if it's a point data set, it's very easy to drop into a voxel, but if you're looking at sort of like a data set that might be broad or general over a wide geography, are you using like any particular like algorithms to separate those out, or what's your like strategy to reappropriate data across like multiple voxels when you're looking at, for example, you were talking about these the building, the grid cell, the cluster, and the trade area.
So the trade areas are a good example here, just because they themselves are shape files, right? This is an isochrone, so a set of dots defining the overall surrounding of a grid cell or a building. And by the way, the building itself is also a shape file. That's a polygon that we overlay to the grid structure, to our database. So basically, the grid database itself, as I said, it can drill out to like kilometers or larger, or it can drill down to dots. So what we do when we overlay with shape files is just we take as small grid cells as possible and then attribute them to the shape file boundary. So at the end, all the calculations are still run on the grid cell level on our database. However, we split it into portions by overlaying with shape files. If there's some averaging that's applied to this grid cell or to this shape file that we cannot reattribute to our grid cells, let's say there's a census tract with some average information on household income level, let's say. So this can be just shown by this polygons, by this not by the grid cells, but by this census tract. So we just transform our grid cells in this case into these polygons, and then we see all the data aggregated by these polygons. I don't know if I explained it correctly or clearly enough, but we have our own dashboard. It is on our website, but I'll share the link. But besides this dashboard, there's also the tool called Inclusive Growth Score by Mastercard. It's actually the tool made by administrative boundaries. In the US, these are census tracts. In the UK, these are postal codes, I believe. And in other areas will be different administrative boundaries. So actually the whole tool is based on our technology, on our platform. And we just reattribute it to these administrative boundaries in this case, while our own dashboard is in grid cells. And so we just, in the cases of different occasions for visualization purposes specifically, we would be using these different versions of the dashboard, let's call it.
Yeah, thanks so much. I think that's clear. One other quick question is, and maybe I missed this because I also arrived a little bit late, but are you doing forecasting as well, and prediction modeling with this data as well, to show maybe like 5 or 10 year expected trends? Because I'm sure you now have many. I don't know how many years back your data goes, but that would be very interesting to understand, what sort of models you're using to forecast out, and what sort of how you would use forecasting on what you're thinking.
Mm-hmm. So we actually are avoiding the word forecast, I would say. So probably my short answer to you would be no, we don't do forecasts. We don't try to look too much into the future, like, prolong the trend, extrapolate. We don't do extrapolations. We, however, do fill the gaps. So we can populate like what we discussed with Laura, we can populate the area that's not populated by anything by a master plan related activity, right? And see how it will be living in case it's built. But this is, I wouldn't call it forecasting because it's not directly the forecast in this case. This is more kind of scenario modeling, let's say. So we play with what if we build something here. So we also, within this voxel kind of database, we created an algorithm that could predict one data layer based on another one. Let's imagine you have all grid cells filled with one data layer, and then another data layer has the blanks somewhere. And so we can try to fill up the gaps by using this other data layer. So that's some voxel-based analysis that our technical team created. And if I find the presentation now, I'll share that. But generally, yeah, those two types of analysis are what I can call close to prediction, to modeling, but this is not forecast. And the data goes back to 2018 with certainty, and can be longer in history, like 2017, 2016, but harder to process. So we mainly work with really the patterns from 2018, 2019 as pre-pandemic, and then 2020, 2021, and now as, current.
Mm-hmm. That's great. Yeah, so it's almost like a form of imputation for missing data in the past that you're working with. Right. Yeah.
And I really found this presentation. It was at NVIDIA conference, so I shared this in the chat, so you can watch the video. That's our data scientist, data lead speaking there.
Oh, amazing! Thank you.
Well, I think we are good. Really, thanks a lot, Katya, for this super interesting thanks for taking the time to answer all the questions. Also, thanks to all of you, to all the urban AI experts for attending the session, for asking the questions. It's really great to see all those familiar faces. So the recording of this session will be very soon available, probably today or tomorrow on our YouTube channel. An analysis of the conversation will also be available on our Medium blog next week. And next week, we will also have our next urban AI conversation. This time, it will be about night governance and urban data, so another fascinating topic. So, and yeah, of course, Katya, if you have additional information, feel free to use the Slack to share your presentation and maybe other elements regarding the Q&A session.
Absolutely. Thanks very much for having me. And that was an interesting conversation. Thank you.
Thank you.
Everyone. Have a good day.
Bye, everyone. Bye, everyone. Bye.
Thanks, Hubert, as usual. Hubert, are you going to be at Autonomy tomorrow or not?
No, I have a final exam.
Okay. Interesting. I didn't have any specific question. It was more like a curiosity.
Yeah, it was really interesting, really great.
Yeah, it's definitely. I know some other companies that are doing these kind of things. When I was working in that think tank, moving on think tank, they have one workshop on real estate and how you can aggregate the data from the cell phone of the people and anonymize it to foresee how the quarter can evolve and what would be the need in terms of mobility.
No, that's really good. I didn't have time, but I wanted to ask her a question about the 15-minute city, because obviously with this tool, you could do like really great analysis, urban analysis, but maybe I will ask on Slack.
Definitely, you should. Thanks, Hubert.
Bye, Aurélien.
See you soon. Bye-bye, guys.
Bye, Alain.